Chapter 12 introduces us to kind of our next level or next leap in statistics, where we'll take a look at examining regression analysis. Next, let's take a look at establishing some definitions for regression analysis. First, let's take a look at the scatter plot, and its definition or its description is a graph on the coordinate plane. And that means we've got an x and a y axis, which contains 1 point for each pair of data. So where our value on our y-axis and our value on our x-axis intersect, that gives us our 1 point for each pair of data. Next, let's take a look at the independent variable. The independent variable is placed on the x-axis. So remember, the x-axis value represents the independent variable. This variable causes a change in the dependent variable, also known as the predictor variable or the explanatory variable. Then we have the dependent variable, and that's the value placed on the y-axis. This variable changes in response to the independent variable. It's also known as the response variable. So the independent variable determines the dependent variable, or the dependent variable responds to the independent variable. Let's take a look at how we would draw a scatter plot. To draw a scatter plot, we take our collected data and we put it on a plot. And here we have an example of hours of study, from 0 hours of study to 5 hours of study, and then the grade received, or test grade, based on those hours of study, from 72 to an 88. So of course we make our grid with our hours of study on our x-axis and the test grade on the y-axis. So our independent variables are on the x-axis and our dependent variables are on the y-axis. The number of hours studied determines the test grade received. So let's begin plotting our data values. For 0 hours of study, we have a test score of 72. And we'll continue on with half an hour studied, or 0.5, would give us a test score of 84. Hours of study, once again, of a half an hour, or 0.5, would give us a test score of 68. This is our collected data. And so on and so forth. You can see how we're plotting on our x and y axis the data values. So this is how you would construct a scatter plot. Let's continue on with our scatter plots. We're interested in the relationship on the scatter plot between the two variables being studied. Like any other relationship, some relationships are stronger than others. What is the relationship between the independent variable and the dependent variable? How strong are those relationships? Well, let's take a look at our scatter plots. First, we've got a linear relationship, and that's when a relationship seems to follow a straight line. We can have a positive slope in that straight line, and that indicates that the values of one variable increases, then so does the value of the other variable increase. So when the x value variable increases, the y value variable increases, and that gives us a positive slope. Then we have a negative slope, and that indicates that the values of one variable increase, but the values of the other variable decrease. For example, as the X variable value increases, the Y variable value decreases, and that would give us a negative slope. Now we have a pictorial or a visual representation of the types of slopes. We have the positive slope and the negative slope. As you view the positive slope, you can see that as the X values get larger or increase, the Y values get larger or increase. So as the independent variable value increases, the dependent variable value increases in the positive slope. For the negative slope, as the X values are decreased, the Y values are increased. So as the independent variable decreases, the dependent variable increases. And that's the negative slope. So let's determine the pattern of this scatter plot. To do that, we want to determine whether the pattern of a scatter plot between the two variables would have a positive slope or a negative slope, or not follow a straight line pattern at all. A, the price of a used car and the number of miles it was driven. We would think that would be a negative slope because the price of the car would go down as the number of miles increased. For B, the pressure on a gas pedal and the speed of the car. In this example, as we press the gas pedal and the car would speed up. So that would be a positive slope. B, the shoe size and IQ for adults. No apparent linear relationship at all. A person's shoe size doesn't determine their IQ. At least we don't see a relationship there. Now let's take a look at the correlation or the co-relation between the two variables. A correlation is the mathematical term for the relationship between two variables. We can have a strong linear correlation when a relationship seems to follow a straight pattern. Or we can have a weak linear correlation when a relationship seems to follow a straight line, but the points are more scattered. We can have no correlation when there is no relationship between the variables. So when we take a look at our two variables, our independent and our dependent variable, we want to see, is there a relationship between the two? And that is known as a co-relationship. Is it strong linear? Is it weak linear? Or is there no co-relation? Here are 4 scatter plots demonstrating the plotted points and the type of relationship. In our upper scatter plot, to the left we have a strong linear relationship. We can see the plotted points are in a straight line. Then next to that, to the right, we have a weak linear relationship. We still see the presence of a straight line, but the points are more scattered about. They don't form a more direct straight line. Then in the bottom on the left we see no relationship, no linear pattern at all. And then next to it we see a non-linear relationship. We see a relationship there, but it isn't a straight pattern. It's more of a curved relationship. Now let's take a look at another concept dealing with correlation, and that's the correlation coefficient. We've got 2 types. First, we've got the Pearson correlation coefficient represented by the symbol rho, and that's the parameter that measures the strength of a linear relationship for the population. Pearson's correlation coefficient, population. Then we have the correlation coefficient represented by the symbol R, and that measures how strongly one variable is linearly dependent upon the other for a sample. So the population deals with Pearson's correlation coefficient, and the correlation coefficient deals with a sample. Here's the symbols or the formula for our correlation coefficient. When calculating the correlation coefficient, round your answer to 3 decimal places. Now, just by taking a look at this formula, we know that we would be better served using technology to find the correlation coefficient. What I mean by that is this is a value in which we will find using our calculators, our scientific or graphic calculator. So we have a graphic to determine Pearson's correlation coefficient. And we take a look at whether we have a strong negative correlation where r equals -1, and that's a perfect negative correlation coefficient, or we have a weak or nonlinear relationship where r equals 0, or we have a strong positive correlation coefficient where r equals 1. So using our technology, here's the instructions for a TI-84 Plus calculator. So first we wanted to make sure that all values appear, then 2 steps only have to be performed. What are those values? Of course, they're your x and your y variable values. We press the second key and then we hit our 0. We select Diagnostics On, and that's the key step. Make sure you select the option of Diagnostic On. Then you press your Enter. Then you press the Stat key and move over and select Edit. Then type the X variable values, and you have put them into your list 1. And then you put in your Y variables, and those would be put into, or would have already been put into, list 2. Then you press Stat key, then Calculate, and choose number 4. And that's the linear regression value, AX plus B. And then we press Enter, and that will give us our correlation coefficient value. So now let's take the concept of our linear relationships together with our hypothesis that we covered previously, the null hypothesis and alternative hypothesis testing. The significant linear relationship we're going to take a look at is for the two-tailed test. So we've got our null hypothesis where the Pearson's correlation coefficient equals 0, and that implies that there is no significant relationship. And we have our alternative hypothesis where the Pearson's correlation coefficient is not equal to 0, and that implies that there is a significant linear relationship. Next, the linear relationship for the left-tailed test, and that's where our null hypothesis has our Pearson's correlation coefficient greater than or equal to 0, and the alternative is that our Pearson's correlation coefficient is less than 0. Next, we have our positive linear relationship, or the right-tailed test, and that's for our null hypothesis. The Pearson's correlation coefficient is less than or equal to 0, and for the alternative hypothesis, the Pearson's correlation coefficient is greater than 0. Next, for our test statistic, we have our t-score formula where our correlation coefficient is divided by the square root of 1 minus the correlation coefficient squared divided by n minus 1, with keeping in mind that our degrees of freedom equal n minus 2. Now that's different. Keep that in mind. We've been accustomed to seeing degrees of freedom equals n minus 1. But as we find our test statistic for correlation coefficient using our t-score, note that the degrees of freedom equals n minus 2. To determine if the test statistic calculated from the sample is statistically significant, we will need to look at the critical value. Also, when using technology such as the TI-84 Plus calculator, the p-values can be compared to the level of significance. So let's take a look at the rejection rule for testing linear relationships. First, significant linear relationships for the two-tailed test. We want to reject the null hypothesis if our t-score is greater than or equal to the t-value of alpha divided by 2, our level of significance divided by 2, because we've got a two-tailed test. Then we want to take a look at the linear, negative linear relationship, or the left-tailed test. We reject if the null hypothesis if the t-value is less than or equal to the negative t alpha. Then we have our positive linear relationship, or our right-tailed test. We reject the null hypothesis if the t-value is greater than or equal to t sub alpha, which is our level of significance from our alpha score. So what are the steps for hypothesis testing? Number 1, state the null of alternative hypothesis. Set up the hypothesis test by choosing the test statistic and then determining the values of the test statistic that would lead to rejecting the null hypothesis. Next, we gather the data and calculate the necessary sample statistics. Then we draw our conclusion. 4 steps. Now let's take a look at determining the level of significance with some examples. So here we want to determine whether the following values of the correlation coefficient are statistically significant. In our first example, we have r equals 0.52. So our correlation coefficient we found on our calculator is 0.52. The number of data values is 19, n equals 19. Our level of significance, or alpha, is 5%. So r sub alpha equals 0.456. So the answer is yes. Our correlation coefficient is statistically significant. In our next example, r equals 0.52, n equals 19, but alpha, our level of significance, equals 1%, or 0.01. R sub alpha equals 0.575. So no, our correlation coefficient is not statistically significant. Our third look at significance is r equals a negative 0.44, n equals 35, and alpha equals 0.01, or 1%. So r sub alpha equals 0.430. So yes, our correlation coefficient is statistically significant. So let's take a look at an example by collecting some data and determining the level of significance at a 0.5 level. So we want to determine this significance. Determine if the correlation coefficient r is statistically significant at the level of 0.05. So we have the number of tickets, and we've collected data 0 to 8. We have the GPA from 3.6 to 1.7. So we have n equals 15. We've collected 15 data values. Our correlation coefficient that we found using our calculator is a negative 0.587, and our level of significance that we've decided upon is 0.05. So our R sub alpha equals 0.514. So that means that we have a statistically significance if the absolute value of our correlation coefficient is greater than R sub alpha. And so we take a look at that. So our R is a negative 0.587, but remember we're taking the absolute value, and yes, it is indeed greater than our R sub alpha, or our level of significance of our correlation coefficient based on our table. And so therefore R is statistically significant at the level of 0.05. Now we have another concept dealing with the coefficient. We've got our coefficient of determination. The coefficient of determination has the symbol R superscript 2, and that is the measure of the amount of variation in Y explained by the variation in X. We know that X is our independent and Y is our dependent. So our coefficient of determination measures the amount of variation in Y explained by the variation in X. Let's take a look at an example of coefficient of determination. If the correlation between the number of rooms in a house and the price is R equals 0.65, how much of the variation in price can be explained by the relationship between the two variables? So if R equals, or correlation coefficient equals 0.65, then our superscript 2, or our coefficient of determination, we take our correlation coefficient of 0.65 and square that, and that gives us a 0.423. So we can say that about 42.3% of the variation in the price of the house can be explained by the relationship between the two variables. And those two variables are the number of rooms in the house and the price. Now let's take a look at our definitions. If R is statistically significant, then a regression line can be used to make predictions regarding the data. So for our first definition, regression line, and that's the line from which the average variation from the data is the smallest, also known as the line of best fit. There is only one regression line for each data set, so there's only one line that is the best fit between the data points. Here we have Y sub hat, and that means it's a predicted value, equals B sub O plus B sub 1 X. Now B sub O is our y-intercept, and B sub 1 is our slope. And so you can see that we're using linear algebra. Other commonly used regression line formulas are as follows. Y sub hat, or the predicted value, equals mx plus b, or y equals b plus mx, or y equals ax plus b, or y equals a plus bx. And you may have seen one of these if you've taken the intermediate algebra class, in which you had to find the slope and the y-intercept. As mentioned earlier, and these concepts in Chapter 12 were best served using our technology, using our calculator. So here's the instructions for the TI-84 Plus. First we want to press Stat, then over to Edit. Then we type in our X variable values into L1 or our list 1. Then we type our Y variable values into L2 or our list 2. Then we press the Stat key, then over to Calc. Then we choose 4, which is our linear regression, AX plus B. And then we press Enter. And then we know A equals B1, which is the slope, and B equals B sub 0, which is our y-intercept. Now let's take a look at a few guidelines around making predictions. A prediction should not be made with a regression model if, number 1, the correlation is not statistically significant. Number 2, you are using a value outside of the range of the sample data. 3, the population is different than that of the sample data. And those are the guidelines for our predictions. Now let's take a look at some examples where we use our information to calculate a prediction. So we're going to use the equation of the linear regression. So we've got y sub hat, meaning it's a predicted value of the dependent variable. And we have 103.085 minus 1.043x. Now to predict what the average achievement test score will be for the following class sizes, this is what we want to do. If we've got a class size of 16, that means that the x value in our above formula is 16. So we plug that 16 in where we see x. So our predicted value for a class size of 16 is an average achievement test score of an 86. And for a class size of 19, we plug the 19 in where we have our x in our formula. We see that the predicted average achievement test score will be 83, approximately 83. And for a class size of 25, we would have a predicted average achievement test score of approximately a 77. And for a class size of 45, we would have an average achievement predicted test score, which is outside of the range. Since 45 is outside of the range of the original data of 15 to 29, we cannot predict the test score. So this is how we use our technology, our TI or other 84 calculators, find the linear regression formula and values, plug them in, and then use various variables for x to predict the value of y. And that does it for our Chapter 12 section 12.1 and 12.2 material.